Okay, so right. So my first lecture is going to be on the four-dimensional light bulb theorem, and well, that's a theorem about the study of embedded two spheres in four manifolds, and more generally about sort of embeddings of two disks in four manifolds. And so, well, just as a very brief introduction, the study of spheres and other spheres, I mean, that's knot theory, right? I mean, one-dimensional spheres and three spheres, that's classical knot theory. And two spheres in four manifolds, two knot theory, or two spheres in the four sphere, that's a venerable subject that goes back to Emil Artin in the 20s, where he found these spun knots, and already he was able to show, I mean, that's an amazingly rich subject, that sort of for example, every fundamental group of a classical knot is represented as the fundamental group of the complement of a two knot. And so anyway, it's a lot of beautiful work in the subject, and it's just really fascinating, in large part because of just a multitude of techniques that go into the study. But also spheres are right at the foundation of four manifold theory, because in dimension four, well, I mean, it's a theorem, I guess, goes back to Wall in the 60s, that if you have two closed, simply connected four manifolds that are homotopy equivalent, then you can find an H-cobordism between them, and a little bit of the theory of H-cobordisms in the smooth category, descend to dimension four. In particular, you try to like simplify the handle decomposition, and you could concentrate all the uncertainty in the 2 and 3 handles. And with 2 and 3 handles, there's the ascending spheres of 2 handles of the ascending spheres of the critical points of index 2, and which are spheres, I mean, in a 5 manifold in this four-dimensional slice. If you take a sort of a slice between the critical points of index 2 and the critical points of index 3, you see these ascending spheres of the critical points of index 2, and you see the descending spheres of the critical points of index 3. So and in the case where the manifolds are, say, homotopy 4 spheres, you see just a bunch of spheres in S that connect some of S2 cross S2, and so all the complexity of the H-cobordism is really about understanding spheres sitting inside of particular four manifold. So okay, so here's another point, which is, I mean, another point of interest, which is about 60 years ago, Steve and Smale classified regular homotopy classes of maps of 2 spheres into Euclidean space, and more generally spheres into smooth manifolds, and of course, that was sort of the seminal work that led to the glorious Hirsch-Smale theory of immersions and generalized in all sorts of categories. But in particular, in one of the early papers, Smale said, okay, develop analogous theory for embeddings. Presumably, this will be quite hard. However, even partial results in this direction would be interesting. So well, I mean, that's over 60 years ago. And in the 60-year interim, in the world of topology, there's this whole subfield, whole field of study of, of spaces of maps of embeddings of one space of embeddings of one manifold into another manifold, and um, and and that's using some hardcore algebraic topology and homotopy theory, but I should say that if you just restrict this question to say two spheres in four space, there's actually strikingly few sort of positive results in the subject. I mean, there's like a whole fantastic set of results for developing invariants for distinguishing, this type of sphere and that type of sphere, and spheres up to concordance and other properties. But having some condition where two spheres are actually equivalent, I mean, there's strikingly few results in the subject. And so here's one such theorem, which is, well, this general result due to Cerf and Palais, which says that if you have a two sphere in a four manifold, and that two sphere bounds a three ball, then the two sphere is isotopic to standard, in essential two sphere. I should say at the outset that everything I'm talking about is in the smooth category. So, right. So and conversely, of course, so that if you have a standard little sphere, bounds a ball. And so, but besides that, I'd say there's really, it's hard to press to find other sort of positive, general positive results. And so, so now let me sort of dive into the topic. So this talk is about the four-dimensional light bulb theorem. But before I go there, let me talk about what's known as the three-dimensional light bulb theorem. And the three-dimensional light bulb theorem is about knots, one-dimensional knots in S2 cross S1. So here in this top left, here's the way I'm depicting sort of S2 cross S1. The green sphere, that's sort of a horizontal S2, and you go vertically, that's the S1. And so here's the knot, which has the property that it intersects this green sphere exactly once transversely. And the three-dimensional light bulb theorem says that if you have a knot in S2 cross S1 that intersects the sphere transversely exactly once, then it's in fact isotopic to the standard vertical knot. And the proof, well, the idea of the proof is in this picture. I mean, you sort of focus. Whoops, I didn't mean to do that. So okay, so right, so like if you focus on a crossing like here, then you could take like one of the strands and just follow the other strand down until it hits the knot. So you get sort of like this spot over here. And now you use the two sphere to swing that strand around the two sphere and get back to this spot, and then just bring it back to where it was before. So this, using the two sphere, you can sort of change all the crossings. And if you just change enough crossings, you can transform any knot to the unknot. So in this case, you can just transform this trefoil to like standard vertical knot. And you might wonder why it's called the light bulb theorem. And I believe this is a term that was coined by Dale Rolfson. And that's because sort of equivalent formulation is this picture here, which is that here we have like this room, and we have this light bulb that's hanging by this knotted cord. And well, assuming there's enough stretchiness or length in this cord, then you can unknot the cord without moving the light bulb, keeping the light bulb fixed pointwise. And well, here you can sort of see, you just take this bit and swing it around the sphere and change a crossing. And well, I mean, the connection with this and S2 cross S1 is, well, in the S2 cross S1 picture, all the action is sort of in the complement of that sphere, because the isotopy was done fixing the sphere pointwise. So that's a S2 cross the interval. And here we are in this room, and if you take a room and remove the inside of a light bulb, well, that's also S2 cross the interval. So these are really the same thing. So, oh, by the way, I should say that if anyone has any questions, just unmute yourself and just speak up. I mean, especially this lecture, my goal is just try to make things more understandable. So yeah, so please speak up. So okay, so now I want to say the statement of the four-dimensional light bulb theorem. So remember, in dimension 3, we had S2 cross S1. And here we have S2 cross S2. And so S2, this S2 cross point, that's like the green sphere. But now we have this standard vertical sphere, that's like the standard S1, S2 cross S1. And notice this guy has the property that it intersects S2 cross 0 cross point cross S2 intersects S2 cross point transversely in a single point. So the light bulb theorem, if it was exactly analogous, would say that if you had another two sphere which intersected this horizontal sphere exactly once, then it would be isotopic to the standard vertical sphere. Well, that can't be true as stated, because it's easy to construct spheres which have that property that aren't homologous. I mean, you could take sort of the vertical sphere and add some number of copies of the horizontal one, and you're changing the homology class. So, I mean, isotopy certainly preserves the homology class. So the theorem is that, subject to the condition that so if you have a sphere that intersects the horizontal sphere exactly once transversely, and it's homotopic to the vertical one, then in fact it's homotopic. It's isotopic by an isotopy fixing the horizontal sphere pointwise. And in fact, if the two spheres coincide in the neighborhood of the horizontal one, you could do the isotopy, fixing a neighborhood pointwise. And I should say that, well, this was proven, well, maybe I first talked about it around 2017. So about 30 years earlier, Rick Litherland proved that, in fact, there's a diffeomorphism of S2 cross S2, which takes the standard vertical sphere to the other one. in fact, that diffeomorphism is pseudo-isotopic to the identity, whatever that is. And coincidentally, Matsumoto proved this theorem in the topological category. So there's a topological isotopy taking sort of, this funny sphere to the standard one. Okay, so, right. Oh, just got an error message from, so let me just check my screen sharing, sorry. Oh, shoot, I somehow got kicked off the meeting. Let's try this again. Sorry about that. So, sorry, Harry, if you could, oh, let's try this.
Do you need the Zoom ID again?
Oh, no, I've got it, thank you.
Oh,
Thank you.
yeah.
So, sorry, this, oh, sorry, can you make me co-host again?
Yeah, okay.
Thanks. Yeah, sorry, it doesn't recognize them. My iPad's the co-host. Okay, well, I've got a backup plan, which is
just to give me a second. Yeah, okay, yeah, since working. Now your iPad is closed.
Oh, great, thanks, Harry. So there we go. Okay, so yeah, so the four-dimensional, just to remind you, four-dimensional light bulb theorem says that if you have an S2 cross S2, if you have a two-sphere that's homotopic to the standard one and intersects the horizontal one transversely once, then in fact it's isotopic, fixing that one pointwise. I should say that there's a much more general theorem that says that if you have two different two spheres, if you have just a general four manifold, and well, subject to this condition on the fundamental group has no two torsion. In other words, every non-trivial element, there's no non-trivial element of order two. Then if you have two spheres that have a common dual sphere and they're homotopic, then they're in fact isotopic, fixing the dual sphere pointwise. So the dual sphere is the word I use for like this green sphere. It's simply an embedded sphere with trivial normal bundle. And so if you have a given sphere, another sphere is considered to be a dual sphere if it's embedded, intersects transversely once, it's trivial normal bundle. So so the theorem is that if you have two spheres that are homotopic with a common dual sphere, subject to this condition on fundamental group, then homotopy implies isotopy. And so soon after this theorem, Hannah Schwartz, in her PhD thesis, showed, in fact, that this two torsion condition is a necessary one. So in fact, there's a four manifold and a homotopy class with two different isotopy classes with the same dual sphere. And in fact, these spheres are not even concordant. In other words, concordance means that if you have your manifold, you can look at manifold cross the interval, and you look at one sphere, manifold cross zero, not one other sphere cross I. And if you could sort of connect them by embedded sphere cross I, that means they're concordant. So in fact, these spheres aren't even concordant, although if you pass to like a twofold cover, then they suddenly become isotopic. And very soon after that, Rob Schneider and Peter Teitner found the exact condition for when homotopy implies isotopy. And so the theorem is you have two spheres that are homotopic, common dual sphere. Then they're isotopic if and only if some invariant called the Friedmann-Quinn invariant vanishes. And in fact, there's a bijection between isotopy classes and given homotopy classes and spheres and spheres homotopic to the given sphere. And anyway, just a technical point, it somehow lives in the group ring over the two torsion elements modulo some subgroup coming from pi3. And it sounds complicated, but it's actually quite beautiful. And I just recommend you look at their paper and see how it's defined. So, okay, so that's the general light bulb theorem. And in fact, this picture is meant to be a schematic to explain sort of what different classes look like. And so maybe it's a lot to talk about, so maybe we won't get into that. But what I'd like to talk about is to give you some hint as to why this theorem is true, at least the theorem in the S2 cross S2, because, on one hand, this is beautiful general theory, but I think it's this S2 cross S2 case is really pretty, and also it helps to maybe just give you sort of a little hint is how one might think about 4 dimensions, or at least how I do. So here's how I think about S2 cross S2. Well, I think about the first S2 is, okay, S2, but then the second S2 as being sort of an extremely long cylinder with the points. So think of a cylinder with the boundary circle of one, contracted to a point, and the other boundary circle contracted to a point. Or think of just a standard 2-sphere and delete the north and south pole. And what's left, of course, is just an open cylinder. So, I like to think of the second 2-sphere as maybe a really long cylinder with the ends that are sort of just squeezed to points. And so there's sort of a personal reason, as Harry mentioned in the introduction. I spent years of my life thinking about property R, some conditional knots, and that was about sort of relating knots to the 3-sphere versus knots in S2 versus S1, and it turned out that only the standard vertical sphere in S2 cross S1, only a standard vertical knot in S2 cross S1 has the same complement as the unknot. I mean, there's the knot theory of one intersects the knot theory in the other, just basically the trivial knot of each. And so anyway, me personally, I like S2 cross S1. So if you think of S2 cross S2 as S2 cross this one parameter family of S2 cross S1s, you can think of the second two, you can think of S2 cross S1 so you can think of S2 cross S2 as sort of like an interval's worth of S2 cross S1s, except at sort of like the minus infinity, the S1 gets contracted to a point, and at plus infinity, the S1 gets contracted to a point. So therefore, you could think of, if you're looking at a surface, an S2 cross S1, sorry, an S2 cross S2, you could think of that as sort of like a movie of curves evolving in S2 cross S1. And or said another way is you have this factor minus infinity plus infinity, which gives you a way of putting like a height function on S2 cross S2 by looking at this minus infinity and infinity point thing. So right. So if we're thinking of S2 cross S2 as this sort of one parameter family of S2 cross S1s suitably quotiented, then the standard, the dual sphere, the green sphere, you could think of just sitting as like S2 cross point in S2 cross S1 times 0. So in some particular S2 cross S1, you fix the S2, that's your standard sphere. And the standard vertical sphere is just, looks like in each of these slices, just a standard vertical circle. And at the minus infinity end, that vertical circle contracts to a point, and the plus infinity end, it contracts to a point. So, and the reason this point of view is useful is because now that you could think of, again, this minus infinity is a height function, and you could do basically think in terms of Morse theory on the surface. So here's, well, I sort of said this, you can, so we have to get this other idea, like thinking of a neighborhood of this green sphere. So from the point of view of S2 as being like a long cylinder with the ends contracted, then a way to think about, you know, a neighborhood of a point in this 2 sphere is, well, start with like a standard neighborhood, but now send out like a little feeler, and that grabs sort of like the, you know, like the South Pole, so maybe the North Pole, and then send out a feeler South Pole. So in other words, from this point of view, I'm thinking of a neighborhood of the origin as being like a neighborhood of the North Pole together with the neighborhood of the South Pole, together with a little neighborhood of an arc that connects the North Pole to the South Pole. And that's kind of like a funny neighborhood, but it turns out to be useful because you could, you know, just imagine schematically that this dot is your green sphere. Then a neighborhood of your green sphere, you could sort of expand it out to this this type of neighborhood. So in other words, you know, from the point of view of this, the way we're presenting S2 cross S1, we can think of it being like the neighborhood of the green sphere consists of, well, just a standard neighborhood of like that sphere across point, you know, between minus 10 plus 10, but then it then encompasses the whole of the manifold, you know, when you're less than or equal to minus 10, bigger than or equal to plus 10. Anyway, the point of all this is that since the sphere, the sphere, the funny looking sphere called R intersects green spheres standardly, then we could isotope it so that all along here, you know, from minus 10 to 10, it intersects, you know, corresponding sphere cross point standardly, and near the the minus infinity and plus infinity ends, it's also totally standard. So all the activity is now going on between minus 10 and 10, and in this region here, which is like a S2 cross the interval. So all the action is going on in an S2 cross the interval times minus 10 plus 10. So therefore we have like a genuine height function, and therefore we can think in terms of Morse theory of what our sphere looks like. So if you have a height function, you have this Morse function. You have just this product structure, and so you have a map from your sphere to minus 10 plus 10, and you could just perturb the the embedding, so it looks like sort of a nice Morse position. And in fact, you could put it into what I call this normal form position, which is sort of in this world a variation of what Kawauchi, Shibua, Suzuki did for 2 knots in S4 about in the 60s, 50 something years ago. And so this is really pretty, which is that, well, let me just say it in this context. You could sort of arrange the critical points so that, okay, so that all the critical points of index 0 appear at sort of a time, say minus 9. And then, well, I'm making this thing have corners, thinking of it just more PL. But so you can imagine suddenly these 2 disks, well, in addition to the standard vertical circle, these 2 disks appear at minus 9. And then you go up in the 4th dimension to time minus 8. So now you just see, a bunch of circles, nice round circles. And then at time, say, minus 6, you see critical points of index 1. And those correspond to just suddenly adding bands connecting this vertical line circle to this circle, and you could arrange it with this special normal form that if there's k critical points of index 0, then there's going to be k bands of index 1, each band connecting one of the circles to the standard vertical circle. And when you attach the bands, these k bands, then you get this other level where the intersection of the surface is connected. And then there's, well, some more critical points of index 2 and critical points of index 1, so-called fission bands, and then that creates a bunch of unknotted circles which are capped off. So in this way, we can organize sort of the data in terms of these critical points. But the big challenge is this: is that, well, we'd like to be able to cancel all the critical points, and so, well, let me just say this. So I suppose actually, it didn't have any critical points at all. It's still there's still something to do, because this curve over here could just be moving around, and there's no sort of critical points, but you get sort of like a loop in the embeddings of this arc. And anyway, you just hit it with some version of Hatcher's Smale conjecture, and you could sort of straighten it out. And I should say, if buried in this case of no critical points is where we actually use the hypothesis that this R is homotopic to the standard one. Anyway, I should say that Bob Edwards, when I showed him this argument, he was just totally appalled by the fact that I was using Hatcher's theorem. So so I recommend you look at what Bob Edwards wrote. He wrote it sort of a, his version of this proof of the light bulb theorem, and gave a very elementary proof, using some basic facts about embeddings. I mean, relatively. So anyway, so the goal is to cancel critical points. So let's look at this this case where there's exactly 2 critical points of index 0. You can have one happen first, and then you see this next time slice where you see this second disk, and now the first disk looks like a nice round circle, and then sometime later you see this band connecting like the core circle with this circle, say. Now I'm drawing the band relatively simple, but that band could be extremely nasty in this level. So at first glance it seems a little bit surprising that you can actually cancel this critical point of index 1 with this critical point of index 0. And so let me just give you an extremely brief hint why you can do that. And well, let me just tell you this sort of philosophical point. I'm not sure how many of you are sort of involved in like geometric topology, but one feature of geometric topology is you have certain like things like this, and they look like really complicated, but somehow you could like just massage the data so that it looks extremely simple. But as in life, if you sort of simplify something, you often have to pay a price. So oftentimes in geometric topology, you do some operation which totally simplifies the picture, and the cost that sort of makes it really complicated somewhere else. So here we have this picture where this band looks really complicated, and well, I just sort of spare you the details, but you could just do some isotopy and you can make it look, just totally standard. Like at this level 6, two circles that are connected by band. So, but the cost is that if you clean up sort of this level and you do it sort of equivariantly through the through the picture, then the critical points of index 1 look like a mess. Like we've already done sort of this critical point corresponding to C2, but now there's this C1, and the way I drew it before, C1 corresponded to just a nice little round circle bounding a nice little round disk. But when we sort of cleaned up at this different time slice, the disk suddenly becomes extremely complicated. And if you look at the projection of the band down to this level, you see it's crashing into the disk. And in fact, that's sort of the problem. You'd like this band to be disjoint from the disk. And if you could do that, then you could make them, you can actually cancel the critical points. Anyway, maybe I've gone into a little bit too much detail here, but the crucial thing comes out at this moment. I'd like to just disengage this circle over here from this complicated looking disk. Because the fact is that if you have a circle in the 3 ball, then if you have a disk spanning that circle, then you could do an isotopy of that disk fixing the circle pointwise. So up to isotopy fixing disks are unique. Fixing the boundary disks are unique. So if I could somehow move the C2 out of the way, I could sort of isotope the C1 and I could cancel the critical points. Anyway, here's the whole point of this thing. Somehow, if you stare at the C2, there's all these tubes that are passing through. And what I'd like to be able to do is just move them sort of off. And your first glance, you think, oh, like I'm in 4 dimensions. And so I just, move, these tubes a little bit in the 4th dimension and just move it off. But the problem is that the circle is also continues as a circle in the past and the future. So you can't just do a little perturbation of these tubes. But what you can do is do what I call the light bulb lemma, which is this, which is, here's up here, here's like the picture, like the top of the picture on the left. Here's the picture that we see, and we want to sort of, replace it by this picture on the right. But here's where we actually use the fact that we have a dual sphere, because we could basically do the 3-dimensional light bulb lemma by just taking this part, just moving it down to the 2 sphere, swinging it around the 2 sphere and bringing it back, and that's so using the the dual sphere, we can actually do this what seemed like a really illegal operation. So after the light bulb lemma, we can somehow disengage the C2, which originally was sitting over here, and then we could just, then we just kind of move it out of the way and isotope this thing to standard and cancel the critical points. So anyway, this takes sort of a lot of thought, just to absorb these pictures. But I hope to give you, just gave you some idea. And 2 things maybe you could get out of this is if you think of a 4 manifold as sometimes you could arrange this 4 manifold where as a 1 parameter family of 3 manifolds, and then you could have a chance of understanding the data. And the second thing is how the light bulb lemma enables you to do like crossing changes in 4 dimensions. So anyway, so that's really what I wanted to say about this. The proof of the light bulb theorem for S2 cross S2. But there's a bunch of applications of this, and so here are 2, which maybe I'll mention. Say this one and this one, which is that if you just focus on S2 cross S2, just a you have an S2 with a trivial normal bundle, then an application of the light bulb theorem is that if you have essential 2 disk, its boundaries in the boundary of S2 cross D2, then you can isotope it to the standard 2 disk, provided the boundary curve is unknotted in the boundary S2 cross S1. And there's actually a slightly stronger version that you can do this isotopy fixing the boundary point-wise, provided that the disk represents the right relative homology class. And so you could, so you could use this to actually understand that modulo diff of the 4-ball, that is modulo diffeomorphism that's localized in a 4-ball, that diff of S2 cross E2 is pi 0 is trivial, and any 2 diffeomorphisms of S2 cross S2, which are homotopic to identity, or isotopic to identity modulo diffeomorphisms supported in a 4-ball. I mean, it's an open question whether diff 0 of a four-ball, diffeomorphisms of the four-ball, which fix the boundary point-wise, is isotopic to the identity. And sort of another version of the light bulb theorem is that if you have a two disk in the four sphere, and suppose that two disk has this, its boundary is the standard circle. So the standard circle bounds the standard round two disk. So the light bulb theorem says that that you can, if you have two smooth disks, then there's a smooth isotopy taking one to the other, fixing the boundary point-wise. So, right. So anyway, there's some other applications which I don't have time to talk about, because I'd like to talk about something which is sort of a prelude, a warm-up to the second lecture. So crucial to the first lecture was the light bulb lemma. The light bulb lemma allowed you to do sort of crossing changes between embedded surface. And so let me just sort of restate it. So suppose you have suppose you have a surface, a sphere in a four manifold, and that sphere has a dual sphere, and you see this picture where the vertical line is part of the surface, and then you see these tubes that are like linking around it. So what you'd like to do is just do an isotopy that just pulls the spheres across this surface, which is in general a very illegal operation, because this line just continues in the past and the future, and you can't do any sort of local perturbation. But provided you could find a path that say from this point that goes all the way to the dual sphere, and that path doesn't cross these tubes, then you can do this isotopy. So this is sort of the general form of the light bulb lemma. So now let me talk about the failure of the light bulb lemma. So look at this manifold on the left, this manifold M. So it looks like a nice three manifold, right? I mean, a handle body of solid handle body of genus 1 with an open wall removed from the interior. So M is a four manifold, which is exactly this three manifold across the interval. So here's a standard, what I call the standard disk. So you can see at this slice, this three-dimensional slice, you see this arc that goes sort of across. And if you take this three manifold multiplied by the interval, that arc multiplies by the interval, and that's a properly embedded two disk in this four manifold, which is also known as the boundary connected sum of S2 cross D2 with S1 cross D3. So here's a way to construct another two disk. So over here is standard two disk, and here's this thing P is a two sphere. Here you're looking at the projection of the two sphere into this three-dimensional slice, but you could see like this meridian, the equator is sitting there, but maybe the northern hemisphere is a little bit in the future and the southern hemisphere is in the past. So I can create a two. So I'd like to tube this standard disk to this two sphere, right? I mean, we know what that means. I mean, just take an annulus and just remove a disk from a little disk from this guy and attach that one end of the annulus on, and remove a little disk from this sphere and attach the annulus on there. So, but we want to do it in a way that sort of links the sphere. In 4 dimensions, arcs link 2 spheres, and so a tube is like an arc. So you take this tube, and like in the picture on the right, and just link it through the sphere, go around the cell in a fundamental group, now tube it off to the sphere. So original sphere I call, original disk I call D0. The other one I call self-referential disk. And here's the funny thing, which is this self-referential disk is obviously homotopic. I mean, you obviously do a homotopy of this self-referential disk to the standard disk, but in fact, there's no isotopy fixing the boundary point-wise. And you look at this, it looks awfully like the light bulb lemma, because here's this tube, this blue tube over here, and I'd like to just unlink it from the sphere. But the problem is that in this light bulb lemma, there has to be a path from right. So what am I trying to say? So right. So yeah. So this spot over here is the analog of this spot over there. So I want to be able to move this tube across, and to do that, I need a path from where the tube is unlinking to the dual sphere. To do that, I need to go a path through here, which is the unallowed thing. And it's funny that, so the theorem is that this disk is not isotopic to this disk rel boundary. And but in fact, there's a diffeomorphism of this 4 manifold, which takes the standard disk to this sort of self-referential disk. So let me try to give you an idea of the proof. And so here we have this nice round looking green sphere, but this sphere is sort of continuing into the past and the future. So what you should think of that is like being almost like a point. It's going vertically. So it's almost like a free edge, and if you have a free edge on a disk, you can just collapse out the disk. So I can just collapse out the standard disk. I can collapse out the self-referential disk and collapse them out to basically the same thing. So the diffeomorphism is more or less pretending this filled-in ball across I as part of your space, and just contracting in using one disk and contracting out using the other. So this might sound a little bit strange, but actually I think most of you are familiar with this, because if you go down like 2 dimensions lower, this is just kind of like the arc pushing map. So this is in 2 dimensions lower. This is like what's known as the point pushing map. So here's the object of interest, which is the surface of genus 2 minus an open disk. And I'd like to show you a construction of a diffeomorphism of the surface of G minus 2 minus an open disk. And the way you could do that is pretend that the open disk is really there, and use that open disk and like take your finger and, sorry, you can't see my finger, but you take your finger and just move that disk, as you could see, to like, right here, or to here, to here and back. Just move that disk, following some path in the space, and you could see that it does a job on the rest of the space. So what you do is you take this you move this guy around and bring it back, and then just pretend it wasn't there to start with, and that induces a diffeomorphism of your space. And in the context of the self-referential disk to the standard disk, there's you can do sort of an analogous thing. So right, so extremely briefly, since I'm almost out of time, is how do you prove this? How do you actually prove that these two disks are not isotopic? Okay, and here's the idea, which is sort of a warm-up to the next lecture, which is the disk. We know what the disk is. That's the interval times the interval. So if we have an embedded disk, we can think of the embedded disk as a one-parameter family of embedded intervals. So you could think of, well, since these disks are standard near their boundary, we could think of this disk D1 as a loop in the space of embeddings of the interval into your four manifold. So the this D0, the standard disk, somehow corresponds to the trivial loop, and this other disk D1 corresponds to another element of the fundamental group. And so as I mentioned in the introduction when I was talking about Smil, the theory of embeddings of one manifold into the other has gone through like a huge development over these 60 years. But if you go back, well, just a few years later, I mean, Hefflicker made some development, and then in 1972, Jean-Pierre Dax, wrote just what I think was just an awesome paper where he developed this theory of embeddings of one particular manifold into another particular manifold, and the requirement was that the source manifold had to be sort of like a relatively low dimension, had to have a pretty big codimension relative to the ambient space. In particular, Dax's theory applies to the theory of embeddings of arcs into four manifolds. And well, I don't have time to explain this, but but his theory is extremely abstract, or at least to me. I mean, he somehow, it's this general theory, and he couches the answer in terms of some Bordism theory, which he develops, which I don't understand. But in the context of arcs into four manifolds, turns out that if you like read between the lines of what he did, just an incredibly beautiful theorem. And so I wrote an exposition of this, just if you're interested in this paper, Self-Referential Disks and the Light Bulb Lemma, where I prove this theorem. And anyway, just as a glance, you could see somehow the space of maps of embeddings of the interval into a four manifold somehow corresponds to the group, the group ring of the fundamental group, over the fundamental group modulo something coming from pi 3. And so it's not actually the full group of embeddings. It's actually the subgroup I call pi 1 with super D for Dax, which corresponds to fundamental group loops of embeddings, which are trivial when they're viewed as loops in this of just spaces of maps. So in other words, it's it's equivalent to more or less your disk being homotopic to this standard disk. So, so again, sorry, I'm out of time, but there's an analog of the light bulb theorem for disks, and so so I proved that, well, the theorem is that there's a map from, so if you fix the disk and you look at the set of disks that are homotopic with a common dual which lives in the boundary, then it turns out the set of such disks have a group structure, and there's a homomorphism from that to this integral group ring modulo, something called pi3. And so actually I showed there's this homomorphism, and it's surjective, and Daniza Kosinovich and Peter Teichner showed that in fact it's injective, and using sort of some sophisticated theory, actually really understand the space, the actual space of embedded disks up to isotopy, which is pretty awesome. And although I believe it's still like pretty open, like what the general theorem is for disks which have dual spheres that don't live in the boundary but live somewhere in the inside. And so Hannes Schwartz has some interesting results in that direction. Let me mention one more thing. Sorry for being over time, but application of this. Oh, just by the way, I mean, it's the disks are a bit more subtle than spheres because this ambient space has fundamental group Z, and unlike the case where it was two torsion that was causing problems, it's these self-referential disks in the fundamental group that cause problems. Anyway, a nice application, which again is a warm-up for the next lecture, is that there's knotted three balls. So there's knotted three balls in four manifolds. There's actually codimension one knotting. And by knotting, I mean, here's this four manifold, which is like this three manifold across the interval. And here's a disk in a three-dimensional slice. You can multiply that disk times the interval. But remember, but anyway, the claim is there's another three ball, which is actually knotted. It's homotopic to this one, but not isotopic row boundary. And the way to get it is the fact that there's a diffeomorphism fixing the boundary of the manifold pointwise, which takes our D0 to D1. And you could look at the image of this ball under that diffeomorphism. And the thing is that you can't actually, if you were able to isotope the image back to B0, that would mean that you can isotope your D1 to be disjoint from B0. And flip the manifold open along B0, you're just left with S2 cross D2. And now you have, now you have, then you get a contradiction to this application of the three-dimensional light bulb theorem, right? I mean that for disks in the right homotopy class, that homotopy implies isotopy, and in S2 cross D2. So anyway, thank you. Sorry to go over time, and thank you for your attention.
Thank you very much. Are there any questions or comments for Dave's first lecture? What were the applications on page 35?
Oh, okay. So yeah. so here's this nice application, which is, I mean, here's a phenomena in 4 dimensions, which is that many things that are different, so to speak. I mean, for example, if you have 2 smooth homotopy equivalent form manifolds, then they become diffeomorphic after enough connected sums with S2 cross S2. And it's a theorem of Frank Quinn, that if you have a diffeomorphism of a simply connected form manifold, then that's homotopic to the identity, then it's isotopic to the identity after enough connected sum of S2 cross S2s. And so a variation of the theme is that if you have homotopic, if you have 2 smooth 2 spheres that are topologically isotopic, then they're smoothly isotopic after enough addition of S2 cross S2s. And so Walkley, Kim, Melvin, Ruberman, Schwartz, somehow used the light bulb theorem to show that if you had 2 homotopic spheres in a form manifold, 2 smooth homotopic spheres in a form manifold, and their complements are simply connected, then they're actually smoothly isotopic after a single connected sum of either S2 cross S2 or a twisted version of S2 cross S2. And here's, I mean, here's second application to concordance. Maggie Miller showed that if you have an organic, a form manifold without 2 torsion, and you had 2 homotopic spheres that are embedded, but only one of them has a dual sphere, then you could, well, you get a slightly weaker conclusion that the two spheres are concordant. And there's with Michael Klug, they proved sort of a more general theorem along those lines. And in a different direction, I mean, this is already really interesting, is, I mean, this, again, the beautiful theorem, I guess, I think there's the Kawauchi and maybe Shibua, I mean, possibly someone else in the 60s, that, I mean, that if you have a 2 knot in the 4 sphere, and by enough stabilization, you can turn it into the standard 2 sphere with enough stabilization. And stabilization is like stabilization for like Hagar. You know, you take a sphere just to add on, looking like a trivial looking tube. So you just take a sphere, you raise the genus. So that's one way of doing stabilization. And another way of doing stabilization is using this theorem of Smale. The fact is that any two embedded spheres in the 4 sphere are regularly homotopic. They can be homotopic through immersions from one to another. So you can you can somehow measure the complexity of the immersion by, well, you know, immersions and embedding, and then there's a moment where there's suddenly, you know, 2 points of intersection, then there's maybe another 2 points of intersection. So more or less, well, any 2 immersions, any immersion can be, you know, isotoped into like isotopy followed by, you know, finger moves, isotopy, finger moves, maybe Whitney moves, undoing finger moves. And so you might ask, well, what's the relation between these 2 types of stabilization? And well, there was a first result done by Oliver Singe, and using that, Joseph Klug, Rubik, and Schwartz showed that in the context of 2 spheres in the 4 sphere, then this, what they, you know, Cass and Whitney, or, you know, the immersion, the measure of immersion of of complexity measured by immersion plus um, is at least the number of by the stable. If you look at the complexity measured by stabilization versus complexity difference measured by the immersions, then in the immersion one is bounded below by the stabilization. So anyway, those are some applications.
Well, thank you very much. Is anyone else questions? No.
Sorry, excuse me?
Yeah, no. I was asking for questions.
Yeah. So if you have any questions, please ask. And here's the introduction to the.
Maybe I'll ask something really short.
Okay.
So one of the applications about two disks in S4, I don't quite see like at least a dual sphere, or like I don't quite see how that was the corollary of the light bulb theorem. Like, could you explain that?
Oh, so yeah, so right. So so thing is that S2 cross S2 and S4 are closely related in the following sense: is that if you take a knot in if you take a simple closed curve in S4, then the complement is S2 cross the interval. So if you take a simple closed curve in S4 and you just remove a neighborhood of it, and you just glue in an S2 cross S2 in the right way, then that transforms S4 into S2 cross S2. And if you start with S4 and you have this curve and you have like the standard 2 disk, then when you do this sort of surgery, well, then that will take the standard 2 disk to the standard vertical 2 sphere. So so that's or you can almost say well more directly, if you could just think of this as the standard 2 disk, and well, since we're in 4 dimensions, a regular neighborhood of the circle is S1 cross B3. So the boundary of B3 is S2. So that S2 is similarly like your dual sphere.
Thanks.
Yeah.
Okay, thanks Dave again for the beautiful lecture. So Dave, we didn't really have a break. So how about we start in 5 minutes?
Okay, 5 minutes.
Yeah.
So
let's resume in 5 minutes, 11:20 in Korean time.
Okay, so let's stop this. Okay, I'm back. Thank you for your patience.
Yeah, hey Dave. So let's continue the second part of the lecture.
Okay, so so thanks for coming back, and so so as you see, I found this KAIST robot pictures on the internet, and so the second picture is sort of a picture of the robot, the innards of the robot, and so this the second lecture is going to be sort of, I try to get sort of more of the innards of sort of what I'm going to be talking about, which is sort of knotted three balls in four space. And as we saw in the first lecture, that well, you know, as far as I know, that's the first example of a knotted ball and three ball and some four manifold. And but it takes some considerable more effort, at least for us. I mean, to construct knotted three balls in four space, and that's the goal of this lecture. So, and by the way, I mean, you know, the original, you know, the official program calls for whatever lecture for such and such time, and then there's questions. But if you have a question, you know, please, I mean, you know, that's, please speak up. I mean, you can see, you know, once I get going, I'm sort of in my own world a little bit, but please, you know, speak up. So just remind you that we'll say a ball is knotted. Say, and if the ambient space is Sn, we'll say that the ball's knotted if the boundary of the ball is like a standard n-2 sphere, and but the ball's not isotopic relative boundary to the standard n-1 ball. So I, you know, here's like classic dimension. So if we're in n equals 2, then you can look at, you know, here's like a random arc that I've drawn, and you know, if you have any knot, you can just sort of isotope it relative boundary to, you know, like the standard one. In dimension 3, well, again, I mean, both these things more or less go 100 years ago. I mean, actually, I mentioned this theorem in dimension 3 that up to isotopy fixing the boundary pointwise, then disks are unique in 3 space. I mean, that's, I mean, more, you could use like Alexander's proof of Schoenflies theorem in dimension 3, at least in PL category. So if you go to higher dimensions, then there's this beautiful book of Hatcher Wagner on pseudoisotopy, and they prove that if for n bigger than or equal to 6, then there's knotted n-1 balls in the n sphere. So that leaves sort of 2 dimensions. I mean, the question about knotted 3 balls in the 4 sphere and knotted 4 balls in the 5 sphere. And so the talk today is about, actually, I should say what I was, oh, sorry. I mean, my motivation for the light bulb theorem to start with, my motivation was really about knotted 3 balls in the 4 sphere. And so, but, so that as a warm-up, I mean, I need to understand knotted 2 disks, you know, 2 disks in the 4 sphere. And so So the Lightbulb theorem is, I mean, two disks are standard. So, but, right. So, yeah, so at the time, I actually conjectured it was not three balls in the four sphere, and well, now it's a theorem. And I mean, independently involved Ryan Budney and myself and Tayuka Watanabe. But if you go for the other dimension, that knotted four balls in the five sphere, well, we sort of, anyway, there's some things that need to be checked, but I'll show you explicitly candidates for examples sort of at the end of the lecture. So, but behind all this is the Cerf-Pillay theorem, which I mentioned. Actually, I stated a very special case of it, but the Cerf-Pillay theorem is basically a theorem about that balls in connected manifolds of any dimension, codimension. Except if a ball is codimension 0, then you need their orientations to coincide. So the theorem is that if you have two K balls in a connected manifold, then there's an ambient isotopy taking one to the other. And here's the key idea. It's sort of very simple, which is, I mean, the heart of the idea is the fact that if you have say a diffeomorphism of n space to n space, which takes the origin to the origin, then there's a very explicit homotopy, which I just right here show you, which isotopes that diffeomorphism to the linear map, which is the derivative at the origin. And well, once you have a linear map, then you could sort of isotope it to the standard one. So anyway, this will come into play in a moment. So as I said, the other lecture, geometric topology, there's often multiple ways to think about the same thing. Well, maybe that's true in mathematics in general. And so here's like three different ways to think about knotted, say, three balls in four space. Actually, since that's the dimension of interest, I'm just being concrete here, but I could just as well have said n balls in n plus one space. But so here's three equivalent formulations. First, you could look at knotted three balls. You could just look at like three balls with the standard boundary in S4. Or you could look at S1 cross B3, and S1 cross B3 is the standard horizontal three ball. And you could look at other three balls which have the same boundary. Or you could look at pi 0 of diff of S1 cross B3, which you can look at isotopy class of S1 cross of diff of S1 cross B3, which fix the boundary pointwise, modulo diff of B4 fixing the boundary. So in three, you're looking at diffeomorphisms, which we'll say they're equivalent if you could isotope one to the other modulo a diffeomorphism of the four ball. So let me try to get the idea across of why these are sort of the same thing. And so kind of like, you know, going from S4 to S2 cross D2 by surgering circle, you can go from S4 to S1 cross B3 by surgering the two sphere. So if you have a standard two sphere in four space, the complement is S1 cross B3. So if you remove a neighborhood of the standard two sphere, then you're left with an S1 cross B3. and you could just sort of just glue in an S1 cross B3 and sorry. If you have the standard 2-sphere and 4-space, and then just remove the neighborhood of that 2-sphere, then you're left with S1 cross B3. So in that manner, you can see there's a direct correspondence between balls with a fixed boundary and balls in S1 cross B3. And on the other hand, suppose you have a diffeomorphism, which fixes the boundary pointwise. Well, you can look at what does that diffeomorphism do to a horizontal B3? Well, that's another B3 which has the same boundaries, since by fiat it fixes the boundary pointwise. So, but the other direction is sort of interesting, is if you have sort of a 3-ball in S1 cross B3, which has a standard boundary, then in fact, it's the image under diffeomorphism. And the reason simply is because let's look at the formulation in terms of knotted 3 balls in the 4-sphere. Suppose you have like the standard 3-ball, and now you have like another one with a standard boundary. Well, Cerf Palais tell us that if we're allowed to move the boundaries, then these balls are ambient isotopic. So we could start with the knotted ball and use the Cerf Palais theorem to isotope it to the standard ball. And then when we're done, well, we have the original 2-sphere, and we could have arranged it that the 2-sphere comes back to itself pointwise. So that's kind of like the point pushing business. So Cerf Palais tells us that given any 2 3-balls with the same standard boundary, then there's a diffeomorphism of the 4-sphere which takes one to the other. And now if you translate that back to what's happening, you can see that translates back to saying that 2 different balls in S1 cross B3 differ by a diffeomorphism. And finally, if you have a diffeomorphism that fixes a ball of S1 cross B3, then you could arrange to fix the neighborhood of that, say, standard ball, and the complement of that is just a B4. So 2 diffeomorphisms fix. So right. So anyway, I've attempted to explain how they're all related, and interestingly enough, that these are all actually abelian groups that you could just compose diffeomorphisms, but maybe this is easier to see in the S1 cross B3 formulation. But if you have a 3-ball, you could sort of have it sort of localized. I mean, just totally standard at some spot and just avoiding the vertical. So basically, you inside of S1 cross B3, you can just take little sub S1 cross B3s and just replace a given ball by knotting it at a little spot. So anyway, so this is some like basic background information. And Hatcher and Hatcher-Wagner in 72, I mean, they weren't thinking at all in terms of like knotted balls. It was all about diff of S1 cross Bn, and that was sort of a beautiful application of computing pi0 of that, as an application of their pseudo-isotopy theory. So here's another basic thing, which is sort of at the foundation of what we're talking about. And we have the following exact sequence. So, well, Well, we have this following map. So if you have a diffeomorphism of S1 cross S3, this little 0 is supposed to indicate that you're looking at the subgroup of diff, which are homotopic to identity. So if you have a diffeomorphism, you could ask yourself, well, where does the standard vertical circle go? So that induces a map from diff to embeddings of S1 into S1 cross S3. The little 0 is meant to be embeddings where the S1 is homotopic to the standard S1. So, but it turns out that this fits in a fiber sequence, and the fiber is diffeomorphisms of S1 cross S3 that fix S1 cross a point. So now you do the long exact sequence in homotopy for bundles, and you get the sequence where pi1 of embeddings of S1 to S1 cross S3, you go to pi0 of diff. Well, I'll just skip a step here. If diff S1 cross B fixing the boundary, and that goes into pi0 diff S1 cross S3. And well, since we're in codimension 3 here, homotopy implies isotopy. So this term is equal to 0. So, right. So this sequence will come into play in a bit, but I wanted to mention it now. And so here's our theorem, which is if you look at diff 0 of S1 cross S3 modulo diff B4 fixing the boundary, then this is infinitely generated group. And also diff of S1 cross B3 that fixes the boundary modulo diff B4, that's also infinitely generated. So using these other formulations, consequence is that there's not 3 balls in the first sphere, and there's also knotted separating S3s in S1 cross S3. So right. So are there any questions? This is like our basic. This is sort of like what I want to try to explain. So anyway, feel free to jump in, but everything that we're doing is very explicit, and this picture on the right is it's an explicit picture of a knotted 3-ball viewed in the S1 cross B3 formulation, and this picture on the left is a knotted. Well, we conjecture it's a knotted 3-ball. As far as I know, it's still open. So let me try to decipher this picture. So we know in 3-manifold topology that there's this operation called surgery, which is if you take a solid torus and you remove the solid torus and then re-glue it back in, that's like 3-dimensional surgery. And 3-dimensional surgery can, well, for certain like integral surgery, then that could be viewed as the result of a 4-dimensional operation. So if you take a 3-manifold, maybe 3-manifold across the interval, and say attach a 2-handle to like 3-manifold across 1, then at the 4-dimensional level, of course, you're attaching a 2-handle. But if you look at what it does to the boundary, that corresponds to a surgery. So, right. So here, this picture on the left, we're starting with the standard delta 0. It's supposed to be like the standard 3-ball. Now the sigma is just supposed to be like a standard looking 2-handle that's being attached inside of S1 cross B3. And it's being attached to sort of like one side of it. And on the other side, there's another, so actually, I should say it's a two handle attached with a zero surgery. And on the other side, there's another two handle attached with the zero surgery, except that the two handle itself is sort of, you know, it's like you have the self-referential picture where this, you know, the neck of the two handle sort of goes around and sort of links, it sort of links itself. It sort of goes through like, I mean, you know, a two handle is kind of like a thickened two disc. And kind of like in the first lecture, we saw how to attach a cylinder connecting a cylinder to a sphere. So you can think of here, this part as a sphere, and now here we're attaching the two handle over here, and it sort of goes through, and now it links this two handle, and now it connects to this sphere. So this sphere together with this tube, that's a two disc, and that's defining the two handle. So so from the point of view of the three ball, what we see is the Hopf link, and we're attaching a two handle to one component of the Hopf link, sort of above, and we're attaching a two handle to the Hopf link other component below, and these are all with the zero framing. So from the B3 point of view, we're doing zero surgery on both components of the Hopf link, which just takes the three ball back to the three ball. But if you view this as what it actually does as embedding in the four manifold, we get this sort of funny picture on the left. Now, that's the one we don't know how to do, but for whatever reason, there's this more complicated picture where instead of zero surgery, you know, attaching handles, framed handles to the Hopf link, we have three separate Hopf link, you know, three split Hopf links, like a Hopf link here, Hopf link here, Hopf link there, and we're attaching handles, zero framed handles to these Hopf links, and since they're separated, again, that takes us back to B3. But it's kind of a nice picture where here we have this two handle, and this is like the first two handle, and now here's the second one on this side, and it comes up, and when you attach a two handle to like a three manifold, you know, it's sort of the inside of the two handles sort of like emptied out. So there's room for it to sort of like nest inside of this two handle. And then there's this one nesting inside of this one, nesting inside of that one. And then in the other direction, this one is sort of just coming around and making this. And then this two handles nested inside of this one, and this one's nested inside of that. Anyway, you have to stare at this for a bit. And this is sort of some explicit pictures. So my goal is to explain this, give you at least a hint. But before I do that, let me spend like 2 minutes, maybe 3 minutes on like a primer on like mapping spaces. I mean, you know, for maybe like 40 years, we go into lectures, you know, as a graduate student and where people would talk about, you know, diffeomorphism groups, mapping spaces, you know, exact sequences, and they're treating them as like CW complexes. I really never understood this. I mean, I even gave lectures where I just said the words, but anyway, here's the basic facts that you need to know, which is that there's this theorem, I mean, first done by James Eales in 58, CR category later by this guy Leslie, and a few years later, C infinity, and that is that that if you have two, a compact manifold and another manifold, and you look at this space of C infinity maps from X into Y, then with the C infinity topology, then it turns out that's what's known as a separable Frechet manifold, which translated means it's a complete Hausdorff space with the topology is induced by countably many semi-norms. Semi-norms is a norm, except that different things with the norm take on different non-zero value, but semi-norm you could have like take on value 0. But the way to get semi-norms is you have this mapping, and okay, you have to make sense of this using local coordinates, but the difference in the partial derivatives and the where they go at the C0 level, that there's like this whole collection of ways to measure different things. And anyway, partition of unity, all this stuff, you can show that it's what's known as a separable Frechet manifold. And using that and some hardcore like point set topology, you could show that this space is C infinity. The C infinity maps from X to Y is homotopy equivalent to a CW complex. Okay, so the reference for that is this paper by Palais, Homotopy Theory of Infinite Dimensional Manifolds. And there's one spot where he doesn't quite prove this statement, which is a little bit annoying, but he says it's maybe dominated by CW complex and refers to Whitehead. If you go to the reference of Whitehead, it's in this like 80-page paper, which I couldn't find where he was referring to, but this is clean exposition by Hatcher in his appendix. Anyway, so if you just with this, you could just with confidence just do stuff with mapping spaces, just like there's CW complexes. So so now I want to sort of like dig into this, and so the question is, how do we get candidates for elements for diffeomorphisms of S1 cross B3? And here's the way we do this: is start with S1 cross S3. We look at the standard vertical circle, and we could. And as I mentioned in the last lecture, thanks to Dax and actually, people after him, that the space of pi1 of the space of embeddings of the circle into S1 cross S3 is understood, at least at some level. So I mentioned this exact sequence. So a loop of embeddings of the circle in S1 cross S3 induces a diffeomorphism of S1 cross B3, which fixes the boundary point-wise. So that's exactly this point pushing business, right? I mean, we have the circle, it's standard, and now we just like move it around, and then we just bring it back to where it started. So that induces a diffeomorphism of the complement of the circle. So it's kind of like, you're making a cake, and there's the spatula, it's the blade, it's sort of like right in the middle of the mixing bowl. And now you take your spatula and just sort of like just stir it around. You stir up your cake, but then bring the spatula where it's started. So that induces sort of that mixing is a sort of diffeomorphism of the complement of the spatula. So in the same way, if we have an interesting loop, we can get candidates for diffeomorphisms of the complement. So, right. So I just sort of like state explicitly here that we have a map phi from the pi1 of the embeddings of the circle and the pi0 of diff S1 cross B3. So as far as I know, this is I will call it a conjecture. I mean, certainly Ryan and I, this is a conjecture, but it was stated, claimed as a theorem in version 2 of our paper, but it's so it's okay. So, but nevertheless, that let's look at some generators let's look at so Ryan and I sort of computed a set of explicit generators for the space for pi1 of embeddings of the circle and S1 cross S3. So here there we'll call them theta 2, theta 3, theta 4. And what it simply is, you start with a standard vertical circle and send out like this band, one time around. And now you get to this spot over here, and you swing this arc around this arc. So here's sort of like a detailed picture over here, where again spheres link arcs. So here's a sphere over here, and here's an arc. So this band, so like this little arc over here just follows the band till it gets to over here, and now this arc follows this, fixes its points, and like at the north and south pole, and then like swings around the two sphere, and then it comes back. So we prove that these are sort of generators. But as I mentioned, I mean, Dax sort of looked at this, and he actually explicitly said in his paper that that the space of embeddings of this S1 cross S3 is infinitely generated. And Greg Arone and Marcus Zimic a couple of years ago gave sort of a more modern proof of that. So, okay, so now, the first step is to get candidates by sort of stirring the spoon around, and now we have to sort of translate these pictures into explicit diffeomorphisms. So it's all about point pushing. So we can do that for, I mean, here's the picture in dimension 2. We just saw that in the other lecture. Here's a simple case where this point here spins around that point. But the thing to note, though, a little bit sort of extension here of what was before, was the support of this particular point pushing lies in this like pair of pants, the disk with two disks removed. In other words, two-dimensional regular neighborhood of like this eyeglass, one complex. So now let's go up a dimension. So in dimension 3, we could fix a point, and now we could swing an arc around that point. And again, you can check that the support of that isotopy is in this solid torus with an open ball removed. So the hull, so to speak, with a solid torus comes from removing the arc, because after all, it's what's happening outside the arc, and this two sphere this ball comes from like removing this neighborhood of this point. So moving the neighborhood of the arc neighborhood of the point gives this, which is the support of this arc spinning around a point. Okay, so now we go up to the dimension of interest. And here we look at a three-dimensional slice. This three-dimensional slice sees, it's the same picture we saw before with this point and this arc spinning around the two sphere. But now, since we're in 4 dimensions, this point extends to the past and the future. Actually, this little thing is sitting in the 3-dimensional slice, but the point itself is going in the past and the future. So in this case, the support of this arc spinning about arc is well, you could take just the ball, the 3 ball, remove 2 inner 3 balls, and multiply that by an interval. So that's a 4-dimensional regular neighborhood of what we call the barbell, which is essentially just two spheres connected by an arc. And so this spinning of arc about arc induces a diffeomorphism of the neighborhood of the barbell, which fixes the boundary of the neighborhood pointwise. And this diffeomorphism is what we call the barbell map. So here now we explicitly translate our loop in embedding S1 in our 4 manifold into what we call barbell implantation. So the barbell, again, I've sort of redrawn the picture, is over here, two spheres with a bar. So in the picture on the left, you could see a 2 sphere over here, and now the bar sort of goes up, and here's another 2 sphere. So these are the two spheres, and this is the bar, and the bar is sort of linking through the 2 spheres, 3 times. And this turns. So the claim is that the induced diffeomorphism from this loop of the arcs spinning about arc, this element of fundamental group of embeddings in the circle in S1 cross S3 is what we call this barbell implantation. And by barbell implantation, that means it's the diffeomorphism induced by embedding the barbell neighborhood in the 4 manifold in some manner, like I have here, and pushing forward the barbell map. So, right. So, right. So so we've gone to step from loops of circles to diffeomorphisms of S1 cross B3. So remember at the end of the last lecture, the way we understood that, able to show that a certain disk is not isotopically standard is we thought of that disk as a 1-parameter family of arcs. In the same manner, we can think of a 3-ball as a 1-parameter family of disks. And so, and we get a diffeomorphism, a 3-ball uses a loop in the space of embeddings of the disk. So here you can actually see, in the first part top, this actually shows explicitly what this loop of embeddings is for the barbell map. So here, this over here, this is well, the barbell neighborhood is this three manifold across the interval, and now there's this three disk, which is this two disk across the interval. So you could ask, well, what happens to that two disk? And I think it's sort of pretty actually, which is you can. So let me show you actually an explicit loop. You take this thing, and you take your hand, and you get to muted myself. So you get to this picture here, and where you squeeze this guy down to a ball with a little neck, and then this sort of disc. So like squeeze to create a neck, and then holding the ends of the neck fixed, swing the neck around this two sphere, and then swing it back, and then just come back to where you started. So that's how to understand. So in principle, we can understand how to view a potentially knotted three ball as a one parameter family of disks if we know the implantation, and here I've shown you what this one parameter family restricted to the implantation is. So it turns out that we never figured out how to use one parameter families of disks. But as we saw in the first lecture, a disk is a one parameter family of arcs. So if you have a one parameter family of disks, that corresponds to a two parameter family of embedded arcs. So an embedded, so a knotted three ball, or potentially knotted three ball, gives an element of, well, a representative for an element of pi2 of embeddings of the interval into S1 cross B3. So that's the way we go about things. So yeah, so sorry, I'm running out of time to explain this, but so here you can see this on the top. This is the one parameter family of disks I just described it. But it turns out you can express it more symmetrically. Somehow there's in the top version, it seems to be sort of asymmetric left and right, and so you can make it more symmetric, and then you could sort of slice it into disks. So right. So now to actually be able to try to, okay, so we have these candidates, and we want to show that they're non-trivial, and the way we go about this is to look at the induced two parameter families of arcs. Now, as I said, the theory of embedding spaces has really developed over the last 60 years, and extremely impressive, but from my point of view, very, very abstract, homotopy theory, which I don't understand. So to make this accessible to like very concrete things, we had to sort of express, develop a theory of two parameter families of arcs and form manifolds, and almost certainly it could be sort of translated back into the abstract theory. And I should say independently, Donna Kostinovich, starting with her 2020 thesis, has been trying to, taking a different point of view, developing sort of geometric theory of embedding spaces. So let me at least try to show you, explicitly what a two-parameter family of embeddings of the interval look like. So, well, maybe this is the easiest to describe, although it's not really the most fundamental one, is this what we call the EPQ family. So here, the horizontal, that's our base arc. And the P represents like this band is going P times around, we're talking about S1 cross P3. So it's going around the S1 direction P times. So it goes around and it spins around the neck of this Q, which is of this other band, which is going Q times around the S1. Anyway, you have to stare at this a bit, but the support of spinning this arc about sort of this one and this arc about that one, the support of those spinnings are disjoint from each other. They're kind of like ships passing through the night. So you can do like one, like over here, the blue first. You can do the red. You can do the red and the blue simultaneously. You can do the red first and the blue. And the funny thing is that if you look over here, you're just doing the blue, but the red hasn't even moved. So you're just basically spinning around thin air. So you could like homotop that loop of path of embeddings to make it trivial. So anyway, I've attempted to explain. Give you an explicit example of a two-parameter family of embeddings of the arc. Anyway, it turns out this simple, beautiful, our opinion, way of understanding two-parameter families. And anyway, we have this bracket operation, but we also can express this all in terms of chord diagrams. I just don't have time to explain this, but somehow, anyway, it's the this for example, this chord over here is suggestive going around the S1 direction P times and spinning around this arc and coming back, and so in this picture here, the blue is symbolic of like the blue spinning, and the red is symbolic of the red spinning, and if blue is not moving, then you can homotop the red way, and if red's not moving, you can homotop the blue, but they get in each other's way. And it turns out there's this interesting relation between this is what called the GPQ family, and there's some relation. So anyway, to make a long story short, is as we saw before, we can express the our loop of maps of the circle in S1 cross S3 corresponds to barbell map. We understand the barbell map as a two-parameter family of maps of the interval, and it turns out that like this, if you have like theta k implantation, it factors into k minus 1 two-parameter families, that look sort of like this. And it turns out that each of those two-parameter families factor into k minus 1 by k minus 1 families. Right. So, I mean, you get, and each of those families, entries factor into, things like this called like DPQ. And there's some of them are just expressed purely in terms of chord diagrams. But to sort of, just to make a really long story short, is we have this barbell implementation. That gives us two parameter family. Each two parameter family factors into K2 minus 1 two parameter families, each of which factors into which can be expressed as sum of entries of K minus 1 by K minus 1 matrix, where the entries are in terms of these GPQs. So you have this whole glorious set of things. You have this massive computation. You add up all the entries of all these matrices, and you get a matrix. Well, entry-wise, you add up the various entries of the various matrices, and you get this skew symmetric matrix. And the final answer is the summing, the entries of the skew symmetric matrix. So, a skew symmetric matrix, the ij entry is negative of the ji entry, and when you add them all together, they all cancel out. So we've made this enormous calculation, and we get 0. So let's call it bad. So what do we do? So after getting over some whatever, that we suddenly realized that this is the barbell implementation, but we can sort of twist the barbell implementation in certain ways. I mean, here we have like the bar going through the sphere, and we could just go make this thing. The problem is the barbell picture is too symmetric, and we could break the symmetry by putting sort of twists around crossing changes, so to speak, of the bar and the cuffs. That's what we call the cuffs. And the effect of doing this change is various row and column operations. And so by doing these row and column operations, we break the symmetry of the matrix. And anyway, we find these guys, delta 4, delta 5. So this is a particular, you can see here's the barbell sort of implanted in S1 cross B3. And so the claim is, our theorem is that these are actually linearly independent and give linearly independent elements in the space of embeddings of the circle of, rather, in pi2, the space of embeddings. So how do we actually prove such a thing? So here I'm going to be very brief, but here we really have to invoke some more modern technology in the theory of embedding spaces, and the theory of embedding spaces, which was maybe that has its origins in the work of Tom Goodwillie and John Klein and Michael Weiss. It's fantastic theory, and so it turns out that if we could understand, you could understand pi2 of embeddings of the arc into S1 cross B3 by looking at pi5 of embedding of the third configuration space of S1 cross B3. So by configuration space, I mean ordered. The third configuration space is triples of points, or ordered distinct triples of points. So right. So anyway, by somehow just seeing what we're doing here, we see that there's the subgroup of pi2 of the embeddings generated by these GPQs using some, there's a isomorphism more or less into pi5 of this configuration space modulo some relation, which is exactly these GPQ relations. Amazingly, the theory on the right sees the GPQ relation as does the one on the left. So anyway, there's just, if you look in the paper, there's like two different ways we sort of do this. And but let me just say a quick technical point is it turns out that the third configuration space, well, suitably compactified, is a 3-simplex. We have 2 parameters. So that's a 5-ball. And a 2-parameter family induces a map from the 5-ball into the third configuration space of S1 cross B3. But what we really want is an element of pi5. So we have to somehow deform the map so the boundary goes to like a base point. And there's some ambiguity in that which gives rise to the relations that I mentioned. And interestingly, these GPQs correspond to sort of Whitehead products in the third configuration space. And right, and I should mention that Donza Kusinovich has analog of this mapping, in her theory. So that's sort of, show you a pretty picture of it really is like one version of some pretty hardcore calculation. So right. So anyway, to summarize, we have this theorem that that diff, if you look at pi0 diff S1 cross B3 modulo diff B4, that's an infinitely generated group. And in particular, there's infinitely many knotted 3 walls in the 4 sphere. Now, we actually claim this theorem about S1 cross S3. So remember, we have this fundamental sort of exact sequence coming from the fiber sequence of pi1 embeddings into pi0 diff S1 cross B3 into pi0 diff S1 cross S3. And we had this homomorphism. I mean, as I try just to give you some hints about of pi0 diff to S1 cross B3 into pi2 of the embeddings. But remember, the bad thing was we did this enormous calculation and everything turned out to be 0. But now the bad thing is the good thing, because the kernel of this map from pi0 diff of S1 cross B3 to pi0 diff S1 cross S3 is pi1 of embeddings of circle in S1 cross S3. So all the diffeomorphisms that come from this term over here, I mean, map to 0. I mean, that was the bad thing. So therefore, by basic fact about group homomorphisms, if we have a homomorphism from some group to another group, and we have a quotient, and the kernel maps to 0, induced map on the kernel 0, then we get sort of induced map on S1 cross S3. So this shows that in fact S1 cross S3 has infinitely generated image. So right. So anyway, that's anyway, using that lemma, Tadayuki promotes what he did to also understand diff of S1 cross S3. So sorry, it goes like really fast, but and there's an enormous amount of details, but I hope I gave you the gist of it. And so again, here's sort of our concrete picture of what these three, well, the picture on the right is what this three-ball looks like. In fact, this is corresponds to a knotted S3 and S1 cross S3. On the other hand, you can look at this picture on the left. This we conjecture is knotted in S1 cross B3, but you can see that this part over here is like hooking around this arc. But if we extend this to in S1 cross S3, we could use the S3 to sort of undo that linking. So this guy is distinctly standard in as viewed in S1 cross S3. So right. So just two quick things. I'm sorry so far over time, but as I mentioned, well, basically from 100 years ago, we understood that knotted one balls in two space and two balls in three space are standard, and there was missing two dimensions: three balls in four space, four balls in five space. So here's a candidate for knotted four ball and five space. And so Ryan and I sort of generalized this theorem of barbells into barbells in higher dimensions. And but so here we are in dimension 5, and so in dimension 5 we could look at, well, the classic barbell, which is two spheres connected by an arc, and dimension 5, two spheres link two spheres. So we can link them, but now the barbell, since we're in 5 dimension, it's thickened up into like a 5-dimensional thing, and we have a barbell map of 5-dimensional barbells, and we could implant it. And anyway, this is our candidate for knotted four balls in 5 space. And one more thing, which still need to be sorted out, but one thing about hyperbolic geometry, an incredible factor of hyperbolic geometry is that if you have a manifold of, the loose form of Mostel rigidity is that hyperbolic metrics of manifolds of dimension 3 and higher are unique. But the thing is, what's not said is unique up to what? And Mostel's theorem says that if you have two metrics on a hyperbolic manifold of dimension n bigger than or equal to 3, then there's a diffeomorphism of the manifold with metric 1, well, an isometry, manifold with metric 1 to manifold with metric 2, and this isometry is homotopic to the identity. What Mostel doesn't say is that this isometry is isotopic to identity. In other words, that in the space of metrics, that these metrics can be connected in the space of hyperbolic metrics. They certainly can be connected in the space of Riemannian metrics. And well, I guess it's classical two-dimensional topology and Teichmüller theory that space of hyperbolic metrics in two dimensions is contractible. So I proved this 20 years ago, actually. Harry was kind enough to mention that the Smale conjecture for hyperbolic 3 manifolds. I mean, that's this theorem. But you can, so that's so a version of that is if you have a closed hyperbolic 3 manifold, the space of hyperbolic metrics is contractible. But on the other hand, if you go to high dimensions, Farrell and Antonada showed that in dimension 10 and higher, the space of hyperbolic metrics isn't even connected. And so anyway, we conjecture that in fact all dimensions bigger or equal to 4, the space of hyperbolic metrics is not connected. And I guess, and the idea is that if you have a geodesic, then a neighborhood of a geodesic in hyperbolic space. Okay, a simple closed geodesic, that's like S1 cross Bn. And well, you can modify S1 cross Bn by you can modify, you can construct a diffeomorphism of the hyperbolic manifold by being the identity outside of this neighborhood of the solid S1 cross Bn. And inside the S1 cross Bn, just stick in sort of a non-trivial diffeomorphism of the right type. And anyway, that's actually, it turned out that's what Farrell and Antonida did in dimensions bigger than 10, but anyway, we have reasons to believe that in fact it should work in dimensions bigger than or equal to 4. So using our barbell maps and so on. So anyway, thank you for your attention, and sorry to go over time, and thank you for the invitation.
Thank you very much. Is there any comments, questions? I guess I missed a little bit of the connection between this knotted balls with the conjecture on the last slide.
Oh, okay. So yeah. So here's a funny thing, which is that yeah. So for example, in this construction, we constructed non-trivial diffeomorphisms of S1 cross B3. But if you looked at S1 cross open B3, then it turns out that these diffeomorphisms are, in fact, any diffeomorphism, I think, of S1 cross open B3 is properly isotopically standard. And the reason is, it's like, this, the telescoping argument, like 1 minus, we tell our students like 1 minus 1 plus 1 minus 1 plus 1 minus 1. We group the terms, and we show that that 1 is equal to 0, right? Because if you have 1, then we add minus 1 plus 1, minus 1 plus 1, minus 1 plus 1. And then we regroup the terms and everything cancels out. So in the same manner that a diffeomorphism S1 cross B3 is it's localized in an S1 cross B3, but now if you have the open S1 cross B3, you can have the diffeomorphism here, and then you can put like its inverse supported in a little vertical S1 cross B3. And then you can have the original map and so on. So you could pair like, the diff with its inverse, an infinite sequence to them. That's a proper map. And then you could just do the cancellation. Well, that's a proper map too. So you could just cancel it out. So why did I say that? So okay, that's still like one thing to keep in the back of your mind. And another thing is, I didn't say this, but these diffeomorphisms of S1 cross B3 or even S1 cross S3, they have the property that when you lift to a finite sheeted cover, then they become isotopically standard. So, well, I'm not sure how much you want to hear about this, but you might like this, which is that if you have, so let's imagine like imagine this in say S in a hyperbolic four manifold, and you have this closed geodesic, and now you just do a barbell implantation in it, and now you've changed the diffeomorphism. Now, we pass, if we have a hyperbolic space, we can pass to the covering space corresponding to that closed geodesic. So that covering space, has fundamental group Z. It's generated by the closed geodesic, and has the feature that closed geodesic, lifts one-to-one when you lift to the cover, but all the other translates are lines. So in the pre-image of that closed geodesic has one component, which is the closed geodesic, which maps one-to-one, and all the other components map infinite to one. So the fact is that, since these diffeomorphisms become standard when you lift a finite sheeted cover, that when you lift to this Z cover, then in the tube that corresponds to the original lift, that one you have the same diffeomorphism, but the others are infinite to one. So what I'm saying is that you can isotope the map in this covering space to one where it's totally supported in that single closed geodesic, and all the others, after preliminary, isotopy, which moves points finite distance, becomes standard. So, and one of the incredible things about hyperbolic space is that it compactifies, like the hyperbolic ball compactifies, and the hyperbolic. And the problem is, so if you pass this covering space, that's the open. It's diffeomorphic to the open S1 cross B3. But what's incredible about hyperbolic space is that, well, the compactification of the ball, projects down to this compactification of the S1 cross B3. So you really get, it compactifies to the closed S1 cross B3. And actually, this is something that goes back to Poincare, and literally in the same paper where he defined the Poincare conjecture, or Poincare question at the time, was, he just throws this as a little offhand remark that if you have, in modern language, if you have diffeomorphism of a surface that's homotopic to the identity, then when you lift to the universal cover, the induced map on the boundary at infinity is identity. And so, of course, the same argument works, in higher dimensions too. So the upshot is that using the hyperbolic geometry, we can lift this diffeomorphism to one which on S1 cross B3, which fixes the boundary point-wise. So we're literally back to this, studying the same diffeomorphism. But there's a little technical point, which is that you know, we're looking at the space of embeddings of smooth arcs, and there's an issue of continuity at right along the. I mean, it's distinctly continuous. Anyway, you know, these two parameter families, you can look up there, but one, you know, things that we need to still sort out, that we need to check that these things are really null homotopic in the space of smooth maps of arcs into S1 cross B3. However, subject that they can be continuous at the endpoints. And so anyway, there's this technical thing which, so anyway, that's maybe that's more than you wanted to hear, but it's I feel like hyperbolic geometry. It's,
Right. Yeah. Yeah. Thanks a lot. Oh. Do you have other questions? If not, let's thanks our speaker again for the beautiful lectures.
you know, thank you very much, and thank you for the invitation. It's a pleasure to, you know, be able to talk about this. And so anyway, I hope you found, you know, everyone found, you know, some points that are, you know, interesting.
Yeah, thanks a lot. It must be very late for you now, right?
Well, we're
approaching midnight, I guess.
yeah. Well, I sent you a message that was, you know, after midnight for you, and you replied. So so I guess maybe by your standard, it's
well, still, but giving a talk is different things.
Yeah.
Yeah.
Actually, I didn't want to say this earlier, but I got sort of a, you know, I guess a second booster today.
Oh,
so it hasn't affected me yet. Maybe it won't at all, but I made a point of just trying to be as late as possible. Here's the previous one, you know, it just had sort of, you know, some like mild things over the next 24 hours.
Mm-hmm.
So
oh, well, sorry for keeping you awake until this late time.
No, it's pleasure. It's actually probably really good for me to really be focused on this and not on other things.
The second booster shot means like this is your fourth shot?
Yeah, it's a 4th shot.
Moderna. Yeah. Let's see. What does
so I'm going to be doing some, actually, my first travel, I actually done some travel in February and March, but I'm going to do a bit more, and I thought, you know, maybe just not to take chances. I mean, the fact is it's, and I think this is what happened with the Spanish flu. I mean, it was horrible in 1917, 1919, but presumably it just mutated and into something that was just maybe like a regular flu. I guess for some people it's still really bad, but I mean, you know, even now, I mean, in the US, I think the flu takes out maybe 100,000 people every year. So, but on the other hand, you know, if it mutates out of it, thankfully, and you have these shots that make it less, then okay, it's guaranteed that if we haven't gotten it already, we'll get it again, and maybe again and again. But
Yeah, I mean, it's getting weaker and weaker in terms of when they
Yeah.
read. So. Well, then this weekend I'll take my first international trip since pandemic.
Okay, so where are you going?
I'm heading to Paris.
Okay,
It's been
that's great. So
yeah, it's been already.
okay, that brings up an interesting question, which is, I presume you fly there, but the route, I mean, is the Soviet Union closed off to?
Right. That's a good point. So my flight will be 2 hours longer than usual because we have to avoid Russian territory. Yeah. So yeah, it will be. I don't remember how long, but like something like 13 or 12 hours, something.
So I guess you just go like a southern route, just
Yeah. Just a little bit detour. I guess we're passing through Turkey.
Yeah. Anyway, have a safe trip.
Yeah, thanks. It's going to be a long flight.
So as of about a few days ago, there's the mask mandate for public transportation in the US was, some judge ruled that it was sort of an overstep of the Center for Disease Control in the US and anyway, Biden didn't seem to be too upset about that. So I think it's essentially optional. I mean,
I see.
So, but for me, I'm being very careful. I mean, I still, with other people and meetings and stuff, certainly travel in the near future, just be masking up, but everybody has their own decisions.
Yeah, I think that we still have the mask mandate, but I think the government plans to lift it to make it optional maybe a month from now or something like that.
Yeah, but Korea, my understanding is, did a lot better than the US. I mean, just keep the numbers down till things sort of,
yeah, until recently. I don't know, like I think that by now probably like about a half of population already got COVID at least once. So
yeah. So yeah, what I'm really nervous about is my plan is to visit Valentin Ponaru in like May, and he's incredible. He's over 90, and he's still like really focused on math. I mean, it's something to me I just really aspire towards. And so, but on the other hand, I mild or not, I just don't want to have it, when I'm there. And so maybe the thing I should be less cautious now, just catch it and be done with it. But
yeah, I mean, I think if you can avoid it, you should avoid. I mean, it's still something. So
yeah. No, I mean, I'm definitely in that school. But
yeah.
So anyway, thank you very much for the invitation, and I hope I wasn't too technical. It's so interesting. So,
it was absolutely beautiful. Thank you very much.
Yeah, thanks.
Let's keep in touch.
Okay, take care. Bye.
Take care. Bye.